Okay, so in the last lecture I was trying to convince you that we will have to study meromorphic functions on the torus, which are especially the simplest of which are a function which has a pole at only one point, which is a pole of order 2, okay. And so let me go back and write down, just recollect what I told you last time, but the purpose of this lecture is to actually show that there is essentially only one normalized, so to say, type of elliptic function on a torus, which is exactly the Weierstrass Phe-function, okay. So let us so let us again recall, very quickly let me say that I have the upper half plane, and there is the quotient of the upper half plane by the unimodular group PSL2C, and we have seen that this is a Riemann surface, and our aim is to show that this is isomorphic to the complex numbers as Riemann surface, okay. And I told you that in general, if you want to even give a holomorphic function from this into C, or for that matter if you want any function, even set theoretic function from this into any set, it is necessarily a function which is constant on orbits, okay. And the orbits correspond to holomorphic isomorphism classes of complex one dimensional tori, and therefore you are trying to find a quantity which depends only on the holomorphic isomorphism class of a torus, and so the point is that looking at a function on this is essentially trying to find invariants for tori, okay. So therefore the point is, what are the tori I am talking about? The tori I am talking about are, well, if you take a point tau in the upper half plane, then you have the corresponding lattice tau gives rise to this lattice L tau, which is the all the complex numbers of the form n plus m tau, where n and m are integers, okay. And then you can take the complex plane and divide by this lattice to obtain a complex one dimensional torus, okay. So this gives rise to T tau, which is C mod L of tau, and of course you know that T tau is a complex one dimensional torus, and the canonical map pi tau from C to C mod L tau, L of tau, which is T sub tau. This is a nice, it's a universal covering map, and the fundamental group of the topological space underlying this torus can be identified with the deck transformation group of this cover, which can be identified with the L tau, which is considered as a subgroup of the holomorphic automorphisms of C, thought of as every element in L tau acting as a translation on C, okay. So essentially I am trying to look at produce for each tau, okay. I am trying to produce something geometric that depends only on the holomorphic isomorphism class of this torus. So I am trying to look for an invariant, and as I was telling you, by the philosophy of Felix Klein, the geometry of a space should be controlled by the functions on the space. Therefore I am tempted to look at functions on this, and I told you that there is no use of looking at if I try to think of a holomorphic function. So so do not confuse this f with this f, okay, or maybe I will even put phi if you want, alright. So if I try to look for holomorphic functions on the torus, that is of no use. That is because if I compose this map, okay, I will get a holomorphic map, I will get an entire function, because after all this map is automatically holomorphic the way we have constructed it. The Riemann surface structure on this is such that this map automatically becomes holomorphic. In fact, it is a locally biholomorphic map because it is a holomorphic universal covering, okay. So this is a holomorphic map, and if this is also a holomorphic map, the composite is also a holomorphic map, therefore you get an entire function on C. And then but then you see this entire function, on the other hand, if you take the image of the function, that is the same as the image of this, but this is a compact set, okay, this is compact, and this is compact because it is the image of the period parallelogram formed by 1 and tau as the vectors 1 and tau as coterminous edges. So the picture is, so I have, so here is my so here is 1 and then here is my tau, and then I have this fundamental, so called fundamental parallelogram, which corresponds to these 4 vertices, which has these 4 vertices, and of course these 4 are elements here in this lattice, and if I repeat this parallelogram on the whole plane, I will get the vertices will give me all the points in this lattice, okay, and the image of this closed parallelogram, that is the interior along with the boundary, is going to be the image of this function, because after all it is periodic, okay. So the point is that you will if I have a function here, then I get a function there, suppose I call it as phi hat, then phi hat, of course, so I put the circular arrow to say that this function is just this followed by this, okay, and phi hat of course has to be periodic with periods 1 and tau, which is the same as, which means that phi hat of z plus n plus m tau should be the same as phi hat of z for all z and for all n comma m integers, okay. This is dictated by the fact that I mean this is just because phi hat goes down to a function, okay, a function above can go down to a function below if and only if it is periodic with respect to this with respect to this lattice, that is the function values are the same if you translate by an element of this lattice, okay. So such functions, so you can see for such a function 1 is a period, okay, because phi of z plus 1 is phi hat of z plus 1 is phi hat of z, and phi hat of z plus tau is also phi hat of z. So 1 and tau are periods, so these are called doubly periodic functions, and the other name for that is elliptic functions, okay. So these are elliptic functions, but trying to require that phi is holomorphic is of no use, because then the image of phi is the same as the image of under phi hat of this closed parallelogram, okay, that is the interior along with the edges, okay. But then that is a compact set because it is closed and bounded, and phi being phi hat and phi being continuous, the image will be a compact subset of C, so it will be bounded, so I will have a bounded holomorphic bounded entire function, and by Liouville's theorem it has to be a constant. Therefore it will not help if I try to look for holomorphic functions on the complex one dimensional torus. I am forced to look at therefore functions with singularities, okay, and of course the mildest singularities one can think of are singularities which are poles, okay. So I can think of functions which have isolated poles as the only singularities, and such functions are called as meromorphic functions, and the simplest case is that I can think of a function with a single with a pole at only one point, and then I have explained to you in the last lecture that if you are going to work with a function which has a pole at only one point, then that pole cannot be a simple pole, it has to be at least a double pole, okay. And then we try to place, so if this function has a pole at the point which is the image of this lattice, mind you all the points in this lattice go to a single point on the complex torus, okay, because they are all in the same orbit of this action by this group of translations. So if you have a function which has a pole at any one of these points of order 2, that is the same as having a pole of order 2 at the origin, alright. And so you know, let me rewrite this diagram in the sense that of course I don't want phi to be holomorphic, I want phi to be meromorphic, so I will put C union infinity, okay, and then I will write holomorphic, and this means that you know, a holomorphic map into C union infinity is of course a meromorphic function, and the inverse image of infinity are the points that correspond to poles, okay. So so you see we wanted a function which had a pole at each point of this lattice, and the pole has to be a double pole. Therefore you know, we cooked up, we were able to guess that roughly, well, if you want a pole at the point n plus m tau of the lattice, then this it should be one simple function that I can write down is of this form, n plus m tau whole squared. This is a pole of order 2 at n plus m tau, and then but then because of periodicity this should happen, if it happens at one point of the lattice it should happen at every point of the lattice. So I will have to take the summation of this over n comma m varying over integers, alright. So I get this family of I get this double series, so to say, of meromorphic functions, okay. Each term is in fact a rational function, okay, and then I have this series, alright. And the fact is that we are so this can also be written as, you know, you can also write it as sigma omega belonging to L of tau of 1 by z minus omega the whole squared. You can write it like this, okay. I can write it like this, and but this, as I will show very soon, this will not give you, as it is, it will not give you convergence, because whenever you write something like this, you write a series of meromorphic functions, you have to put some conditions so that the series converges, at least at the points where there are no poles, because where there are no poles you want it to be an analytic function, okay. So a meromorphic function is analytic except for poles, alright, and the poles have to be isolated, okay. In this case anyway, the grid points, the points of this lattice are of course isolated. So to avoid convergence problems, what one does is one defines the Weierstrass Phe-function in the following way. One defines a phi function associated to this torus, to this tau in the upper half plane, to this associated to this torus as 1 by z squared plus sigma omega a non-zero element of the lattice 1 by z minus omega the whole squared minus 1 by omega squared, okay. So this is the expression. The fact is that, you know, if you forget this minus 1 by omega squared here, then whatever I have written is exactly what is here. The only thing is this extra minus 1 by omega squared is added. I have put this I have taken out this 1 by z squared, okay, because, you know, if I include origin then I cannot put 1 by 0 squared, okay, it does not make sense. So I had to pull out the z squared out, and then I have taken out this contribution as z tends to omega, this term becomes 1 by omega squared, and I have subtracted that here, but of course as z tends to omega this is going to go to infinity because it is a pole of order 2, okay. But the fact is you will see very soon that this is very important to make sure that this converges at all points outside the lattice, okay, we will prove that. So this is the Weierstrass Phe function, and this dictates the point is this is essentially the important meromorphic function on this torus, and it dictates the geometry of the torus, alright. So we will see how that is true in this and the following lectures. So but before that I will have to justify that all this is proper, I mean well defined and so on and so forth. So let me start with a few remarks, okay. The first thing is so suppose suppose f let me say f1 of z and f2 of z, okay. Suppose I take two functions, okay, are periodic, are doubly periodic, or let me say periodic with periods 1 and tau, okay, that is doubly periodic, okay, and let me say that and are meromorphic with a pole of order 2 at each point of the lattice and nowhere else, okay. So you see I am looking at two functions, okay, I am looking at two meromorphic functions on the complex plane, okay. So these so that means you know f1 comma f2 are defined from C minus the lattice to C, okay, and they are holomorphic but for the points on the lattice, and at each point of the lattice they have a pole of order 2, okay. Now so you see what I want to say is that f1 such functions can be normalized in a certain way so that you finally end up getting only one unique function, and that unique function has to be the Weierstrass Phe function, that is called the Weierstrass Phe function by uniqueness, and that function is this one, has a formula like this, okay. So what is that normalization? So the normalization is, well, we will let me think for a moment. So you see in particular, you know, if you the normalization is defined by looking at the Laurent expansion of the function in a neighborhood, in a deleted neighborhood of the origin. See, the origin is of course a point of the lattice and the function has a pole of order 2 at the origin, alright, and if you write out the Laurent expansion at the origin, you see it will be in the following form. So let me write that out. In a deleted neighborhood of 0, the Laurent developments are look, or let me say they look like f1 of z, it is going to be you see it is a pole of order 2. So what I will get is I will get b2 by z squared, z equal to 0 is a pole of order 2, so I will get b2 by z squared plus b1 by z plus b naught plus, let me say, a naught plus a1 z plus a2 z squared and so on. And if I take f2, well, I will have to use so I will put primes. I will say b2 prime by z squared plus b1 prime by z plus a naught prime plus a1 prime z plus a2 prime z squared and so on. The Laurent development is going to look like this. That is because z equal to 0 is this is a Laurent development about centered at the origin, and the origin is not included, so it is a punctured neighbourhood of the origin, and this is the Laurent series development for these two functions, okay. And the point is that these two, so this part, this corresponds to the so called singular part of the Laurent development. The rest of it is an analytic function, okay. So now the normalization condition that I put is I will set the coefficient of 1 by z squared to be 1, okay, that is the normalization condition I put, okay. So suppose we we insist that b2 is equal to b2 prime is equal to 1, suppose you insist this, okay. So this is the first normalization condition, that is you take the elliptic function, alright, and look at the Laurent development at the origin and insist that the singular part contains only z to the minus 2 with a coefficient 1, and in particular it means I am setting b1 and b1 prime to be 0, okay. So let me write that b1 is equal to b1 prime is equal to 0, that is, in other words, the condition is the singular part is z to the minus 2, that is the singular part, okay. In general the singular part will be some constant into z to the minus 2 plus some constant into z to the minus 1. The normalization that I do is that I say the singular part has to be z to the minus 2, okay. Now the claim is that once you do this, then any such function automatically becomes an even function, okay. So that is the first observation, alright. So then f1 and f2 have to be even functions, f1 and f2 have to be even functions. See why? See, for example, see you look at f1 of z minus f1 of minus z. Look at this function, look at the function f1 z minus f1 of minus z. Then you see you will see that if I expand it, what I will get is I will get, you see, I will get a1 so let me write it down. So f1 z is going to be, well, 1 by z squared plus a naught plus a1 z plus a2 z squared plus so on minus, well, f1 of minus z is going to be 1 by z squared plus a naught minus a1 z plus a2 z squared minus and so on. So what I am going to get is I am going to get, the point is, you see, in a neighbourhood of the origin, the only pole that I have, that is removed, okay. So what happens is I simply get 2a1 2 times a1 z plus 2 times a3 z cube and so on, okay. And what is this? Notice that this is an analytic function. The difference is an entire function, okay. It is an analytic function, and see whatever I have done, so I am looking at the origin, okay. I am looking only at the origin. If you look at the difference is an entire function, but on the other hand notice that both of them still have the same periods 1 and tau, okay. if I change z to z plus n plus m tau, and here also if I change minus z to minus z plus n plus m tau, because f1 has n plus m tau as periods, 1 and tau as periods, this is still doubly periodic. So what this computation tells you is that you are having a doubly periodic function which is entire, I mean which has no poles, okay. So see, the point is that this difference is a doubly periodic function, it has no pole at the origin, therefore it has no pole at any other lattice point. The difference function has no pole at any other lattice point, because after all the values of the function are the same if you displace by an element of the lattice, translate by an element of the lattice. So therefore this difference becomes an entire function, alright, which is doubly periodic, and it has to be a constant again by Liouville's theorem. Therefore this is equal to this is entire and bounded. The boundedness comes from the doubly periodic nature. So this will be equal to a constant, okay. So this difference has to be a constant, and the claim is that that constant is actually 0. That constant is actually 0 because if you want, I can put half, put z equal to half, or put z equal to tau by 2, put something either half or tau by 2. So I will get f1 of let us say tau by 2 minus f1 of minus tau by 2, that constant is also going to be equal to this, and this is going to be 0. This is going to be 0 because the difference between these two z values is tau, and tau is a period, and the function does not change its value if you change the argument by, translate the argument by a period, okay. So the constant is 0. As a result, what this argument tells you is that f1 of z is even, okay, f1 of z is even. So the point is, the moment you put the condition that the singular part is z to the minus 2, the function becomes even, okay. So now I am going to put one more condition for the normalization, and that condition is going to be that when you write out this Laurent expansion, I am going to insist that the constant term is 0, okay. I am going to insist, the second condition I am going to put is that the constant term is 0. Suppose, so let me write this here, similarly f2 of z is also even for the same reasons, okay. Now next let us insist that the constant term in the Laurent development at the origin is 0. Let us put this extra condition, okay. So that means, so in this discussion I am saying put a0 equal to 0, a0 prime equal to 0, okay. So you see what will happen is that f1 of z will now have this expansion, it will be 1 by z squared plus a2 z squared plus a4 z power 4 and so on. Mind you, it is an even function, so you have the expansion has to be like this, and f2 of z will be again 1 by z squared plus a2 prime z squared plus a4 prime z power 4 and so on. So this is how the Laurent expansions are going to look like. Now you see, again if I subtract the two, I will get an entire function which is doubly periodic, okay, and therefore it will be a constant, and therefore these two have to be equal, okay. So the upshot of the story is, you take a doubly periodic function, that is an elliptic function with exactly a pole of order 2 at each point of the lattice, you put these two normalization conditions, namely in the Laurent expansion at the origin the singular part is 1 by z squared and the second condition is that the constant term is 0, then there is only one function, and the claim is that one function is the Weierstrass Phe function, okay, and the function is given by this formula, okay, that is the claim, okay. So let me write that down again. F1 of z minus f2 of z is a constant which is 0, so we have shown, so what we have shown is the following, so I can write it here, so maybe I will draw some lines here so that so what we have shown is the following theorem. There is a unique doubly periodic meromorphic function elliptic function with a double pole at each point of L of tau and nowhere else, and whose Laurent expansion at the origin has singular part 1 by z squared and constant term 0, okay. So what I have proved is that there is essentially only one and given this normalization exactly one doubly periodic meromorphic function with pole of order 2 at each lattice point, and with the extra normalization condition that the Laurent expansion at 0 the singular part is 1 by z squared and the constant term is 0, okay. So this is what the discussion shows. Now what I am going to do is I am going to tell you I am going to call that function as the Weierstrass Phe function, that is that unique function I am going to call it the Weierstrass Phe function associated with the torus, okay. So let me write that we call this unique function phi tau sub z and the Weierstrass Phe function associated to t tau or to L tau or to tau in the upper half plane, okay. So this is the we call this unique function as a Weierstrass Phe function. So you must all be wondering that I have written this thing here, so that is going to be the next thing that we are going to show. I am going to show that the right side has all these properties, okay. I am going to show that the right side is a meromorphic function, it is doubly periodic, of course the Laurent expansion at the origin the singular part is exactly 1 by z squared and the constant term is 0, therefore this has to be equal to that is what I am going to do next, okay. So and that will tell you that this is indeed the expression for the Weierstrass Phe function, okay. So let's do that. We next show that the series. So let me give it a name, phi of z. Let me call it as phi of z. Okay, let me call it as phi of z, but I don't want you to confuse that phi with phi hat. So let me call this something. Let me call it as f of z. Okay, so suppose I call this or maybe even s of z, if it helps. Okay, so s of z is that series 1 by z squared plus sigma omega in the lattice omega not equal to 0, lattice omega not equal to 0, okay, of this expression which is 1 by z minus omega the whole squared minus 1 by omega squared. We next show that this series has all these properties and so has to be equal to the Weierstrass Phe-function. Okay, is the Weierstrass Phe-function. Okay, we show this. Okay, so let me do that. So the first thing that I need to worry about is the convergence. The first thing that I need to worry about is the convergence. So you see, let me draw a diagram. So picturing the lattice, so I have so this is my tau, this is one. Let me put it here, 1. Okay, so this is my, so and this is 1 plus tau. Okay, so I have this lattice, this lattice of points repeating themselves. So I'll have 2 and so on and so forth. Okay, and so you see, fix an omega naught in the lattice. You fix an omega naught in the lattice, which is non-zero. Okay, so you see this omega naught is going to be therefore of the form m naught plus n naught tau. Okay, where both m naught and n naught are not simultaneously 0. And let us look at the condition mod z lesser than mod of omega naught by 2. I am going to look at this I am going to look at this this open disk. Okay, so you see, well, omega naught is, for example, some point of the lattice, and you know then this is the vector that represents omega naught, and the length of this vector is mod omega naught, and I am looking at, so mod omega naught by 2 is going to be something here, and therefore I am looking at this disk. Okay, so this is the radius of this is mod omega naught by 2. Okay, and I am looking at all the complex numbers z here, and of course and I am trying to estimate each term of that series. Okay, I am in fact in particular I would like to estimate the term of the series that corresponds to omega equal to omega naught. Right, so let us do that. See, what's the term inside? It is 1 by z minus omega naught the whole square minus 1 by omega naught. Okay, omega naught squared, this is what I have, and if I take the mod of this, what do I get? I get, well, it will be omega naught squared minus z minus omega naught squared by omega naught squared into z minus omega naught whole squared mod, and this will be, well, this is well 2, so it is omega naught minus z plus omega naught into this omega naught minus plus z minus omega naught divided by omega naught squared into z minus omega naught squared, and that turns out to be, well, I will get z into 2 omega naught minus z by omega naught squared into z minus omega naught squared, okay. And if I estimate this, see I will get this is less than or equal to, you see of course I can replace this z by mod omega naught by 2 in the numerator, but I do not do it purposely, okay. So I will keep this mod z as it is. You will see why I am not doing it, okay, the reason for that. So I am keeping this mod z as it is, alright, and this 2 omega naught minus z mod can be written by triangle inequality to be less than or equal to, you know, well, 2 times mod omega naught minus plus mod omega naught by 2. I can write this, okay. I am just using mod of a plus b is less than or equal to mod a plus mod b, and I am using mod z is less than mod omega naught by 2, and of course this omega naught squared in the denominator I am not going to worry about it, and this one, this mod z minus omega naught is by triangle inequality it is greater than or equal to modulus of mod z minus mod omega naught, and that will give me so the reciprocal of that will be less than or equal to the reciprocal of modulus of mod z minus mod omega naught, okay. This is what I will get, alright, and yeah, so I just wanted to say that this can be, so well, this can be replaced by mod omega naught squared by 4, okay, again by using triangle inequality, right. So yeah, right. So so the upshot of all this is I will get well, I will get 5 10 mod z by mod omega naught cube, okay. So I need this, you see if I had replaced this mod z by again by mod omega naught by 2, I will get only a mod omega naught squared, and mind you, your lattice is in 2 dimensions, it is not good to have 1 by mod omega naught mod omega squared and trying to sum it, okay. So now what I want you to notice is that if mod z see if mod z if see, so what I am going, let me say what I am going to write down, if you take any points of the lattice which are outside, okay, I mean which are outside the circle centered at the origin and radius mod omega naught, okay, then it is also true that mod z is also lesser than mod omega by 2, okay, and all these calculation will all this estimation will hold with omega naught replaced by omega, okay. The point is it will hold for all omega that are outside this circle, points of the lattice that are outside this circle, okay, and what is left out are only finitely many points which are inside the circle. So the convergence is essentially a question of whether for all points outside the series converges, okay, and what we will show is that the series is numerically dominated by some multiple of sigma 1 by n squared, which you know it converges, okay. So and that is where we will use this, you will need this omega naught to the cube, okay. So let me explain that. So and of course in all these calculations one is of course assuming that when you sum it up, you are assuming that z is not going to be any one of the, of course not going to be any one of the lattice points, because if z is any of the omegas in consideration, then this term does not make sense because it becomes 0. Okay, so so you see, for all omega in L of tau with omega mod omega greater than or equal to mod omega naught, okay, you will similarly get that mod z is going to be certainly less than mod omega by 2. Okay, this has to happen because mod z is going to be is less than or equal to mod is less than mod omega 2, and that is less than or equal to mod omega by 2. So the same kind of calculation will tell you that 1 by z minus omega the whole squared minus 1 by omega squared, this is bounded by 10 mod z by mod omega cube. Alright, so therefore you see, if I look at this series, I mean tail end of the series, okay, you take omega in L of tau, you take all omega in L of tau with mod omega greater than or equal to mod omega naught, okay, then this series 1 by z minus omega the whole squared minus 1 by omega squared, okay, if I look at this series, this is just that series except for finitely many terms, okay, so that converges if and only if this converges, alright. So and if I look at the absolute series, what I will get is I'll get that this is it is going to be by this estimate omega belonging to L of tau summation over mod omega greater than or equal to mod omega naught, and I will get 10 mod z by mod omega the whole cube. This is what I get, okay. Now what I am going to say is that this is actually going to converge, okay, and for that there's a little bit of geometric insight that is needed. So so here is a claim, since tau is non-real, there exists a lambda greater than 0, a real number lambda greater than 0 such that modulus of n plus m tau is always greater than lambda times greater than or equal to lambda times mod n plus mod m, okay. So you see, this is something that you can immediately think of geometrically, but it is an exercise to verify that this holds. Roughly, you know, if I draw a diagram, at least you should be able to see why this is a result that can be expected, because you see and of course here n and m need not necessarily be integers, n and m could be any pairs of real numbers, okay. So let me write that also, for all pairs of real numbers n comma n. So I am saying real numbers, so in particular it will also hold for pairs of integers, okay. So what does this mean? See, if I draw this lattice, so if I draw this lattice, so you see I have see if I let's assume that say n and m are positive, okay. So you see so this point will be n times 1, okay, and then I will have, if this is the direction of, if this is tau, then I will have some something like this, this will be n plus m tau, okay, and you know, if I this is 1 of course somewhere here, I am assuming n is greater than 1 in this diagram. So if I join this, you see this length is modulus of n plus m tau, okay, and you see if I take modulus of n plus m n plus m tau, and if I divide by mod n plus mod m, I am actually dividing by this length, okay, and by the factor of this length by tau, okay, and you can see that the ratio cannot it cannot go to it has to be bounded below, okay. Mod n plus m tau by mod n plus mod m, that ratio has to be bounded below by something positive, it cannot go to 0, okay, alright. So it's kind of geometrically very acceptable if you look at this picture, okay, but one needs to actually show that this is true because tau is in the upper half plane, so it's a non-real quantity, okay. So this is a small exercise which I will leave to you to do, okay, and let's believe this exercise, then proof of claim is a simple exercise which I will ask you to do, and but let's apply it, okay. So if now consider pairs n comma m which are integers, and n is mod n plus mod m for given n, okay. So look at these quantities, okay. Actually there is a double summation here, I mean there are two freely there are two integers here, okay, but I want to group it into one. So what I do is I look at all those pairs n comma m such that mod n plus mod m is a certain capital N, then how many do I get? I will get 4 capital N such pairs, because for every pair n comma m, the n comma minus m is also another pair, okay, and then minus n comma m is also another pair, and then minus n comma minus m is another pair, so you actually get 4 of them, and therefore there are totally 4 n such pairs, okay. So I should say now consider pairs with this, okay. Then there are well 4n such pairs, there are 4n such pairs, and therefore you see there are 4n such pairs. So you see if you look at if you try to sum over, so if you try to sum over 1 by mod omega cube, if you try to sum over 1 by mod omega cube where omega is is varying in the lattice, omega not equal to 0, okay, then you see this is less than or equal to, alright, 4 is 4 by, so let me write that down, sigma omega in L of tau, so now I'll change it to a summation, n equal to 1 to infinity, alright, I will get 4n 4 by 4 by lambda cube 4n by lambda cube no, I will get 4 by lambda cube into 1 by n cube into 1 by n squared, okay, right, because in fact I will get 4n by lambda cube into 1 by n cube, okay. This is what I will get, and you see and then of course this n cancels, and so essentially what I get is I can pull the 4 by lambda cube out, okay, and I will get sigma n equal 1 to infinity 1 by n squared, which you know converges. And mind you, you see this n above cancels with an n below, so it should have been n cube here. If it had been n squared, I will get summation 1 by n, and that is going to diverge. And why did I get n cube? Because if you go back, I let this omega, I let this z on top remain as it is, okay. If I had replaced this z by mod omega naught, then I would have lost this power of 3 here, I would have got a power 2, and then when I came back here I would have just shown that this is dominated by sigma 1 by n. That's not going to be of any use, okay. So it was very purposeful that this mod z was left as it is, alright. So what does this calculation tell you? This calculation tells you that the the series given by S of z, this calculation tells you that the series given by S of z converges uniformly and absolutely on all compact sets, okay. And of course you should not look at it at you are not worried, I mean you are not looking at the points which are poles, namely the lattice points. Outside the lattice points the series converges, okay. So hence S of z converges at all points outside of the lattice in any compact subset of C, and the convergence is uniform, okay. Now because of the uniformness the resulting function is also going to be analytic, okay. So you do get a function which is analytic except at points of the lattice, okay. So then you have to worry about at the points of the lattice you have to say that each point is a pole of order 2, okay. You have to say that and then you have to say that there is this resulting function here, you have to say that it is doubly periodic, okay. Then you also have to then it will be more or less clear that because of this theorem it will be more or less clear, it will be clear that this has to be the Weierstrass Phe-function, okay. So let us do that. Thus S of z represents a meromorphic function with poles of order 2 exactly at points of L of tau, because you see if you look at points of L of tau, see the same calculation will tell you that you know as z goes close to omega, you can see that so long as z is not omega the series of course converges, but because of this term the limit z tends to omega will become infinite, so it will certainly be a pole. And if you take limit z tends to omega of z minus omega the whole squared into S of z, you will see that will be a non-zero quantity, okay. Therefore z equal to omega each point of the lattice will certainly be a pole of order 2. So so it is certainly a meromorphic function with poles of order 2 at each of those points. Okay. Now the next thing I want to tell you is that this is in fact doubly periodic. Okay. So the trick is as follows. See, you calculate the derivative of S of z. Because of uniform convergence you can do term wise differentiation. Okay. So you do term wise differentiation and what you get, you will get minus 2 by z cube plus summation over omega in the lattice, omega not equal to 0 of well, if I differentiate this I will get minus 2 by z minus omega the whole cube, and I can write this compactly as minus 2 sigma 1 by z minus omega the whole cube with omega in the lattice. Okay. I can also include z equal to 0. Okay. There in the original expression I had to remove z equal to 0 term because I had this 1 by omega squared. Okay. But here that is gone. Okay. So what I get is S prime of z is this. Okay. And this term is because this is summation over the whole lattice. If you translate z by a lattice element, this sum is not going to change. Therefore this is certainly doubly periodic. Okay. This is certainly a doubly periodic function. Okay. So let me notice that S prime of z is periodic, is doubly periodic with period 1 and tau. It is certainly doubly periodic with periods 1 and tau. Okay. That is because you take an element of the lattice and if you translate the lattice by an element of the lattice you are going to get back the lattice, so nothing is going to happen. Okay. So what is the upshot of this? If I take S of z plus suppose I take S of z plus 1 minus S of z. Okay. Suppose I consider this difference S of z plus 1 minus S of z. Okay. And suppose I differentiate it. Okay. I'll end up getting d by dz of this will be 0. Okay, because I will get S dash of z plus 1 minus S dash of z, but S dash is has period 1 and tau, so this will be 0. So what this will tell you is that you know S of z plus 1 is equal to S of z, I mean minus S of z is a constant. Okay, and that constant has to be 0. Now that constant has to be equal to S of minus half plus 1 minus S of minus half, which is S of half minus S of minus half, and this has to be 0 because if you look at the expression for S, from the expression for S it is very clear that S is an even function. Okay, wherever it is defined. So what we have proved is that S of z has 1 as a period. The same kind of argument will show you that S has also tau as a period, because d by dz of S of z plus tau minus S of z will be 0, and that will imply that S of z plus tau minus S of z is a constant, and now I can plug in minus tau by 2. Okay, and so that constant has to be S of minus tau by 2 plus tau minus S of minus tau by 2, and this is S of tau by 2 minus S of minus tau by 2 and that is again 0 as S is even. So let me write it here also as S is even. S is even because of its definition. Mind you, we have not yet proved that S is doubly periodic. So you have to be careful here. Okay, so what we have proved is therefore S is doubly periodic. It's a meromorphic function with poles exactly at the points of the lattice, pole of order 2, and if you look at the expression for S, it's clear that the singular part at the origin is 1 by z squared. So let me write that down. S of z, thus S of z is 1 by z squared plus sigma omega in the lattice omega not equal to 0, 1 by z minus omega the whole squared minus 1 by omega squared is so let me say it in words. It's doubly periodic with periods 1 and tau. It has a pole of order 2 at each of the lattice points, and if you look at the origin, you can see that this is going to be analytic in a neighborhood of the origin, and the singular part is 1 by z squared. Okay, and it's also clear that the constant term in the Laurent development at the origin is 0. Therefore it satisfies all the conditions of the theorem that I stated, and therefore this has to be the Weierstrass Phe function. Okay, so is P tau psi. Okay, so the upshot of all this is that you also have got a nice formula for the derivative of the Weierstrass Phe function, which is going to be very important for us in the forthcoming lectures, because that's going to tell you why the why any complex torus is actually algebraic. Okay, it's going to help us to explain that. So let me also write that down. The derivative is just minus 2 sigma omega belonging to L of tau 1 by z minus omega whole cube. Okay, so I'll stop here.